Okay. Good afternoon, 61C. Good afternoon, 61C. That's better. Okay. So today we're going to steam right on ahead to a different kind of parallelism. We're going to talk about thread-level parallelism and start teaching you about OpenMP, which is one of the standard ways people use the program using threads. You'll be using this in Project 3. But just to review what we did last time, if my clicker works. Last time we started talking about parallelism in general, the idea of Amdahl's law. The Amdahl's law really says that it doesn't matter how much you speed up the parallel sections. If you have a large amount of serial work, that's going to eventually limit your speed up. And it's kind of pretty brutal once you look at the numbers. You really have to almost parallelize everything to get good speed up. We also talked about the Flynn taxonomy, SIMD, MIMD, SysD, and MISD, sort of multiple instruction streams or single instruction streams playing against multiple data streams or single data streams. We then took a look at the Intel, one of the Intel SIMD instruction sets, SSC, which you'll be using in the labs and project. And this is a way of exploiting data level parallelism where a single instruction operates on multiple items of data packed together in these wide 128-bit registers. We also showed you how to access these instructions from the C level, so you don't have to deal completely in assembly code. You can use these intrinsics, which are these C functions that map one-to-one to one of the machine instructions. And the C compiler takes care of allocating values into registers and scheduling and all those other details. But you still have to sort of break things down to this individual instruction level. You just don't have to deal with all the issues in the assembly code. Okay, so that's what we covered last time. So this time, remind you where we are on the stack, we're going to look at a different level of parallelism, which is at the thread level. So this is where you have different processor cores running independent, little independent programs, independent threads, and that's what we're looking at today. So just to give you where does this come from? So this is our classic, simple processor model. You have a processor there with some registers and a program counter. It steps through, executes instructions, fetches data from memory, operates on the data, writes it back to memory. And a multiprocessor is just saying, well, instead of having one processor operating out of that memory, I'm going to have more than one, right? So there's a second hardware processor that's going to be fetching instructions, doing compute, and reading and writing from that same memory space, right? So this is the simple mental model you should start with. Multiple processors, each independently running code, but all sharing the same memory space. So now there's kind of two ways you can use a multiprocessor like this, and we covered this last time. One way is if you have just completely independent programs. So program A, program B, I can just run them at the same time instead of running one after the other. So that's one way of getting extra throughput out of your system, one way to use a multiprocessor. That's for independent jobs, so independent tasks. What we'll be focusing on today is how you make a single program run faster by using multiple cores. So now you have to somehow divide the work of one job into pieces that you can parallelize across different processor cores and somehow make them together run the program faster than a single processor by itself. A bit of terminology. A little while ago when people started building more than one, what it used to be is the chip that you had your processor on was just called the processor because there was only ever one processor on there. As they started adding more processors to the processor, they needed another name for something, right? They couldn't keep calling it the processor chip because they had more processors on there. So what they started to do was call the chip the processor, but call the individual processors on there cores. Like how many cores, how many independent, I still think of them as processors, how many independent processors are there on the chip, and each one of those they call the core. And so you hear the term multi-core, meaning there are multiple independent units that can fetch instructions, run their own program on one chip, instead of just being one on one chip. Right. The original term microprocessor was developed at the point that you could actually put a whole computer on one chip, a whole CPU on one chip. The micro piece meant microcircuit, a single chip holding a processor, microprocessor. Now we have multi-core microprocessors, where there are many cores on one single chip. Okay, so core is just an individual one of those processors. So this is some data that a bunch of people gathered over time, and it kind of shows you what's been happening in the computing industry. And it's a really nice chart, because what it shows you, here's Moore's law. So this is time in years, 1975, 2015, right? Most of you were born somewhere around here, I gather, from last time. And this is a log scale of the number of transistors in thousands, right? So the very first processors only had a couple thousand transistors on them. These days, individual chips may have several billion transistors on them, right? So on a single chip, several billion transistors. So this is Moore's law, the fact that over time, this has been an exponential increase in transistor count. So remember, this is a log scale. This is kind of a straightish line, sort of straight. Now, through most of history, history of the microprocessor, there's just been one processor on that chip. And you may say, wow, why do you need so many more transistors? We used to be able to build a processor just with a few thousand transistors. Why did that one processor need hundreds of thousands or millions or 100 million transistors? Well, what happened over time is we learned how to build more complicated processors that ran a single thread faster. And, for example, we started pipelining the processor. We started adding caches to the processor. We started adding floating point units to the processor. And then as we got even more transistors, we started allowing that one processor to execute more than one instruction per clock cycle, and later to execute instructions out of order in one clock cycle. So all these things kind of soaked up that transistor budget, and our processors got bigger and bigger and bigger in terms of transistors, but physically they were about the same size because they all fit on one chip, right? But over time, we used all that increasing transistor budget to make the processors more complicated and make them go faster. Right, so they were going faster anyway, because as you shrunk the transistors down, the clock rate would go up, and that's another thing you see here. The frequency is just rising and rising and rising. So the smaller the transistors are, the faster we can switch them. So that was one component of performance. Another component was every clock cycle, the processors were doing more work, and that was another way to get more performance. So if you notice that this line is a little steeper than the clock frequency line, so there's more going on than just the clock frequency making things go faster. Sorry, the sequential performance is here, and this is going up a bit faster than the clock rate. However, it got to a point where, as we were doing all these things, packing more transistors on a die to build a processor and clocking them faster, started taking more power. And originally, power was not a concern at all, because we basically couldn't run the thing fast enough for power to be an issue. But as we got into sort of gigahertz range of clock frequencies, power consumption started to rise, and sort of 2000s are kind of when we started having trouble, because around 100 watts or so, 100, 120 watts, is about the limit of what you can easily air cool in an enclosure. So a chip is so big, and there's a certain 100 watts in something this big is kind of like a light bulb, something like that, an old incandescent light bulb, right? And that's something you can conveniently air cool just by having a fan on it. Getting above about 120, 130 watts, it's really hard to take the heat out without moving to some more exotic cooling technology, for example, some kind of pumped liquid technology. And that's too expensive for most applications, and also people worry about getting water all over their server room. So water cooling is really reserved for more exotic supercomputers. So just in run-of-the-mill conventional machines that are air-cooled, you have this limit of about 120, 150 watts for a reasonable fan and air cooling system. So that puts an upper limit on how much power you can dissipate on one chip at reasonable cost. And that's kind of this ceiling you hit here. So what happened was we kind of hit this power wall where things have been going, just growing and growing and growing. Oh, oops, this is too expensive to move up here. And so that started to constrain what we could do with the one chip. And in particular, what it meant was we couldn't just keep making the cores more complicated. Another thing that happened that's not shown here is we started to run out of tricks. So we're using all these tricks to make a single program run faster, executing multiple instructions per cycle, executing them out of order, guessing which way branches were, speculating on, I'm guessing what your answer is going to be. All these kind of tricks we'd sort of started adding them into processors, and you should take CS152 if you want to learn more about all those tricks. But all those tricks, we sort of ran out of steam. It took even more hardware to get very small gains in performance, so it kind of wasn't worthwhile doing this. And for all these reasons, the power reason, the limits in extracting more performance from a single thread, basically the whole industry starting around 2002, 2003, started, instead of having a single core on a chip, putting multiple cores on a chip. Now you put multiple cores on a chip, the way you get more performance isn't by raising frequency. You see what happened was frequency kind of tanked. It started leveling out around 3.5 gigahertz. We had 3.5 gigahertz processors 10 years ago. We haven't really, and we're sort of around that same range now, right? We haven't really gone up in clock rate in a long time. Instead, the way we're getting more performance is by adding more cores. So there's more parallel cores in the chip. Now that only translates into more performance if you can use those cores to give you more performance, right? So the individual cores themselves are only a little bit faster than they were 10 years ago, right? But it's only by using more of them that computers still keep on this curve. So if you look at what's happened to sequential performance, it kind of tailed off here. So running one thing on one processor, how fast does that go? That kind of slowed down. And so to get back on the, these nice and up into the right curves, you have to write apps that are parallel. And these days, pretty much any processor chip you buy has multiple cores on it. Even very small systems like your phones. Your phones have probably at least 2 cores. There's people selling phones with 8 cores in. And actually, if you look inside the chip, there's actually a few dozen other cores you don't even get to see that are doing different things on that chip. So these days, everything you buy has many cores on it, multiple cores on it. And so, looking ahead, especially you guys starting out your career, every machine you're going to be programming is going to have a lot of cores on it. And you have to learn how to harness those to make programs run faster. So the mobile systems, you'll find you have multiple cores and GPUs on those. We'll talk about GPUs use the data parallel stuff we talked about last time, the SIMD-style instruction sets. In large-scale data centers, if you're programming, web apps or programming Google search engines, you're going to use many, many cores over the cluster, each node of which will have many cores on it. So hundreds of thousands of nodes, and each node will have tens of cores on it. That's the kind of scale system you'll be programming. And each of those cores will have SIMD instructions on it. So these multiple levels of parallelism, you have to kind of exploit all of this to get the peak out of the machine. Yep. Is there a way to use these cores programming C? So it kind of has been a holy grail. A lot of people have spent a lot of money and effort trying to figure out how to take an old C program and automatically parallelize it to run across multiple cores. I think that's what the question was, right? Yeah, so if you want to just take all your old serial code and just have it magically run in parallel on these multiple cores, a lot of money's been invested in that. And the answer is occasionally it works, and most of the time it doesn't. Because the way people write the sequential C code, if you want to preserve the semantics of that code and do it correctly, it's extremely hard to do it in parallel. So the reality is you have to kind of go in and restructure your program to make use of the parallel cores. Yep. So we'll be talking about how to program parallel machines in this today. So we'll get around to that. Okay, so really parallelism is the only way to get higher performance these days. And unlike 20 years ago, a lot of what you'd hear in a lecture would be, yeah, parallelism is this niche thing off to the side. Don't worry about it. Sequential machines are just getting faster all the time. It's better just to write good code for a sequential machine and wait for the performance to improve. These days, a sequential program is a slow program, right? The only way to get performance is writing a parallel program. So what's interesting, if you look at how industry's been progressing, they've been both adding more cores and also adding SIMD extensions and widening their SIMD extensions quite a bit. So this is a different way of using up the transistors. Like 10 years ago, you would use up the transistors by trying to build a bigger single core. Here we're just widening, increasing the number of cores and also making the SIMD piece of that core wider. So let's just take a look at, so project 3 you'll be trying to write the fastest code on an 8-core computer that has SIMD extensions. That'll be your project. But if you take a look at what's happening in the industry, so this is partly reality and partly projection. But what's happening over time is the number of cores on a chip is going up slowly. It's like about 2 every year, like plus 2 cores every year, an arithmetic progression. But the SIMD width, which is how wide SIMD stuff can you do in every clock cycle, that's been doubling every few years, right? So we're kind of right around here, 2015, so the order of 14, 16 cores on a die. And the newest Intel parts actually have a 512-bit wide SIMD unit. So one instruction does 512 bits of work, right? You can divide that down into 8-bit, 16-bit, 32-bit, 64-bit elements, but 512 bits total of work being done in each of the units. And this is going to happen. You're going to get to 1024 in another few years. So the AVX standard from Intel is spec'd up to 1024 bits. So it's 1 kilobit of SIMD work from one instruction in one clock cycle. And we'll probably get up to 20, maybe 30 cores at some point, reasonable future as well. Now, if you kind of multiply these together, you get the number of cores times the SIMD bits per core, and that gives you this number, which is kind of an idea of the raw parallel throughput of that chip. Like how many bits of stuff can you do per clock cycle, right? And you can also translate that into floating point operations per clock cycle. So we're getting up into like hundreds of floating point operations per clock cycle on these newer chips, right? And that's what's going to be happening. So the interesting thing is, actually we're going to see a bigger gain in maybe 2.5x. I guess it's looking back a bit, but over 10 years, sort of 2.5x gain in the number of cores, but maybe an 8x gain in the SIMD width, right? So SIMD is going to be a really important component in performance. Okay, so let's focus on threads. So what's a thread? A thread, unfortunately, has many different meanings, both in hardware and software, but it really comes down to a thread is like a flow of instructions that are doing some task, right? So a thread has associated with it a program counter, stepping through some code somewhere, and it has some local data, and it's running some task, right? So that's what a thread is. Now, on the hardware side, each processor can provide, the simplest one is just have one thread, the thread that's running the hardware and the processor. There's one program counter, there's one set of registers. It just steps through fetching and executing instructions for that one thread, and that's how the thread advances, right? You fetch and execute instructions along the thread. So a hardware thread is a processor executing code. I like to use the phrase heart for a hardware thread to separate it from a software thread. So I like to use the phrase heart because it's like a heart. It's always beating. It's always fetching and executing the next instruction in hardware. It's always running. Now, at the operating system level, the user may write code that has many threads in, but those are more virtual, more abstract, and the software will actually multiplex those software threads onto the available hardware threads. So you might have 100 programs running on your laptop, but you may only have 2 or 4 hardware threads in your laptop. And so it's the operating system's job to kind of copy it, move a software thread onto a hardware thread so it can actually run, and then let it run for a time, then it'll chop it off and switch it off the hardware thread, just store it in memory, and it doesn't move at that point. Pick a different thread, put that on the hardware thread, then it runs a different software thread for a while, and then switch it off. So hardware threads actually do work and execute code, right? Software threads are this more abstract entity that you can move onto a hardware thread to run for a while, or switch off a hardware thread to let it sleep and let somebody else run for a while. Okay, so the operating system is responsible for doing this multiplexing of taking all the software threads you want to run and mapping them to the actual hardware threads in the hardware. So I kind of said a lot of this, but so a classic way the operating system works, if you just consider one processor with one hardware thread, it'll start a program running and set a timer off on the side. So the hardware thread will run, execute instructions for this one software task until the timer runs out. Timer runs out, you get an interrupt. The hardware thread then jumps into the operating system, runs some code that saves off the state of the software thread, loads up the state of a different software thread, starts that one running with a timer, and that way you have these little time slices where each job runs for a little bit of time, and the operating system swaps them in and out on the real hardware thread, right? So that's how you share the hardware threads amongst all the software threads. Now, one other technique we'll talk briefly about here is hardware multi-threading. So I mentioned that the simple processor only runs one thread at a time. There's one program counter, one set of registers, fetches and executes instructions for that one hardware thread until it's done. Yep, question? So, so a thread, from a programmer's perspective, when you write code, you don't know how fast it's going to run, right? You just, here's my program, I hope it runs fast. The semantics, the results don't depend on how fast it runs. Well, hopefully they don't depend on how fast it runs. And so you write a program, and then when you run that on a machine, how fast it actually runs depends on not only how fast is the processor, but what fraction of the time do you get to run your program on that processor. And so what happens is we have many programs competing for one processor. When all the ones that are not running are just held in memory. So in memory somewhere you store the value of the program counter, you store the value of the registers. And then when it gets to be your turn, you copy the registers into the processor's registers, you copy the PC into the PC by jumping to it, and then the processor will start from where you left off, fetching instructions, changing your registers, writing to memory. Then when your time is up, the timer will go off, you'll be interrupted, the operating system will come in, it will then save your registers, it will save your program count, where did you get to this time, save that back out to memory, and then you're just sitting in memory as data, while some other thread runs on the hardware processor, right? So every thread can be represented in memory just as a data structure holding the program counter and the contents of the registers, right? And it's that you just copy that in and out to the real hardware registers and run it for a while. That's how you do time slicing on a machine. Okay, so that's how software threads map to hardware threads. But in a processor, you can also build a processor so it can run multiple threads simultaneously at in real time. So, and this was motivated by the fact that processors are kind of expensive components, and you don't like them sitting idle. And say you have a cache miss. So say you have one thread is running, gets a cache miss, hardware thread is running, the processor gets a cache miss. The processor just stops and waits for data to come from memory. Meantime, that processor is just, the hardware is just sitting there and waiting for the data to show from memory. So a thing you can do is provide a second set of registers and a second program counter. And so when one hardware thread takes a cache miss and you're waiting for its data to come back, you switch over and start running from the other context, the other program counter, the other set of registers. So you switch over in hardware to a second thread without saving and restoring to memory like you would do if the operating system was involved, which takes a lot longer. So by doing it in hardware, you can do it cycle by cycle. This is useful for a lot of applications that have a lot of thread parallelism. Yep. Exactly. Yeah. So, right. Yep. So you'd have, program counter 1, 0, program counter 1, 2 sets of program counters, 2 sets of registers. They can share the LU. They can also share the caches, the floating point units, a lot of the hardware. So the amount of resources you need to add is quite small to allow the second thread to be there. And the goal of it being there is just that you can more effectively utilize all the other hardware in that processor core by doing this fine-grained switching between two active hardware threads. And in more advanced machines, actually, the 2 threads run at the same time and cycle by cycle share different resources. That's called simultaneous multithreading. But you want to take CS152 to learn about the details of that. So for now, the important thing to realize is there are some number of hardware threads in a chip that you build, and those are divided into processor cores, and each core may have multiple hardware threads running on it. So some number of cores, each of which has some number of hardware threads. Yep. Right. So this is a core. Like this processor here is a core. A simple definition of a core is something that has an instruction fetch unit and can fetch instructions and decode and execute them. And you have separate cores on the chip. Each of those cores may support multiple hardware threads. Right? And that, in current systems today, it's very common organization. So just to kind of iterate the difference, so multi-threading is, the goal is to get better utilization. We only take a few percent more, a bit more than 1%, more like 5% or something more hardware. But you may get 10 or 20% better performance, 1.5 10, 1.1, 1.2 times better throughput for a relatively small investment in hardware, because you share all these other components that are there already. Multi-core, you actually duplicate the entire processor. So you can imagine one thought exercise, I could either have 2 cores with 1 thread or 1 core with 2 threads. So 1 core with 2 threads is going to be a lot smaller, but the performance improvement is going to be less. 2 cores with 2 threads, it's going to be a lot faster, but it's going to cost you a lot more in area. And in practice, all modern machines do both. So every core has some degree of hardware threading, and then you have multiple cores. Right? That's sort of standard on every machine. And just to point out, my machine, this laptop, if you run this command line command, it'll actually tell you, it'll pull out all the hardware parameters of the machine you're running on. So you can run this right now if you have a Mac. And if you look down, these are the 2 interesting things here. This says you have 2 physical CPUs, and that means 2 cores. There's 2 cores. Each core, and the total number of logical CPUs is 4, because each of those cores has 2 threads running on it. So there's actually 4 hardware threads in this laptop that can all be running at the same time. Okay, and these are some of the other like I have 8 gigs of RAM. These are the cache, 32K cache, level 1 IND, 256K cache, level 2, 4 meg cache, level 3. So you can see all these real hardware parameters of your laptop. Yep. Right. So in a simple system, you'll just switch. So only 1 thread is running at a time, but you'll switch very quickly between them. And actually in this system, it does this simultaneous threading. So actually they're both running at the same time. And the way it works is if one of them needs the floating point unit, the other one needs the load unit, they can both do that on the same clock cycle. So you're running different instructions from both of them on the same clock cycle. So they actually are both running simultaneously. So I don't want to go into details of how that happens. We'll do that in 152, if you take 152. So the machines, I think these are similar to the current machines. I haven't updated this slide. Yeah, I think the current machines are the same. You actually have 8 cores and 2 threads per core, so 16 hardware threads total. So in the machines that we're using in the project. So you should be trying to use up to 16 threads to get the most performance. It's not going to be much point trying to use more than 16 threads in your programs, because what will happen? Sorry? Bottlenecked. Well, what will happen if you say you have 17 threads? What's going to happen? You as a software developer write code with 17 threads in. Yep. Sorry, I couldn't hear. So how are the software threads mapped to the hardware threads? Well, you have 17 running on 16. Right, so depending how the operating system schedules the threads, you can have only 16 can actually run at any time. So 17 threads can have to wait some amount of time, and then it'll swap in and swap out one of the other ones. So there's always going to be only 16 max actually running. So there'll always be one waiting. And so if you've written the code assuming you could have 17 running at the same time, you're going to get very poor performance, right? So at best, you can have 16 running at the same time. The other thing to realize is, if you're running this in the lab and somebody else is running on the same machine, and they also have, say you have 16 threads. Well, I only got 16 threads, you say, so I should be able to get peak performance, but then somebody else logs in and starts a job with 16 threads. You're sharing the same physical resources, so both of you only get sort of roughly half of the cores on average, and the operating system is going to be swapping in and out your different threads, and actually you'll probably do a lot worse than if both of you had ran with 8 threads, only at the same time, right? So when you're sharing the machine, the operating system has to somehow make things work, and it usually does a bad job if more than one job is running at a time with lots of threads. Okay, so administrivia time. So just remind you about, there is a midterm next week, and it covers stuff up till last lecture, so not this lecture. There's a review session April 4th, Gorilla section April 5th, and a HKN review session. Is that scheduled yet?
It's Sunday,
So that's from Sunday from 12 to 3 in HP. So look on the website. It's all up on the website to find the review session. Okay. Okay, let's take a break for a couple of minutes.
저번에 렌즈 맞추려고 렌즈 한국에서는 한 19만 원한테 여기서 11만 원? 그래서 여기서 맞췄는데 막 조금 더 정밀 검사해봐야 될 것 같아요. 많이 안 좋대요. 좀 안 좋아. 별로 안 좋은데 나도 거의 태어나서 나보다 안 좋은 애는 거의 장애인 빼고 있어. 안 보이시겠네요? 안 보이는데 나 라섹도 못해. 이거 피부가 안 보여. 진짜? 오른쪽으로 마이너스 한 몇인데? 기억이 안 나는데? 안 하긴 너무 오래돼서. 와 진짜 하나도 안 보여. 빨간 것도 하나도 안 보여. 나도 안 보인다. 아 진짜요? 내가 10.5거든. 왼쪽은요 형? 왼쪽이 더 나빠요? 왼쪽이 10.5고 오른쪽이 10이야. 천천히 돌리는 거야. 눈도 이거 타고나는 거잖아. 저는 짱눈이어가지고요. 어지러운 거 아니야? 아 진짜? 야 근데 뭐지? 군대 면제 그거 조금 바뀌었던데? 시력 다시? 어떡해요? 시력 면제 수치가 나오나? 그 원래는 그냥 나쁘면 안 됐단 말이야? 근데 바뀌었어. 짱눈이 눈이 장난 아니거든. 어드민이 스테이트에 인수가 있는 거야. 지금 내 시력으로는 원래 면제 됐거든. 근데 그게 이번 년인가 바뀌었어. 면제 안 되는 걸로. 아니 원래 면제 안 되는 건데 면제 되는 걸로 바뀌었어. 정신과 치료 6개월 이상. 진짜 있어.
Okay, let's get going again. All right, so yeah, I was just going to say all the review session information will be up on the website, so check it out. But it'll be on Sunday, the review session, the HKN review session. So we talked about the hardware. So you have this, I told you can have all these hardware cores, all these different threads. You're going to have to use them to get good performance. If you're interested in performance, it's going to be parallel code you're writing. So what are you going to write it in? You're going to need some kind of parallel programming language. And, here's just a small piece of the massive graveyard of dead parallel programming languages. So there's been many, many, many attempts over the decades to develop parallel programming languages, and this is just a few of them. And almost all of these are dead because it's really hard to write a parallel programming language that people like and is widely used and actually is effective. In the class, we're going to use one of the survivors. one of the more popular languages. And it's actually, the reason it's popular is it's just a language extension. So you add it to an existing language, and we're going to be using C, because you know C. So OpenMP, there's a extension to C. And what's also nice about it, it adds minimal stuff on top of the C programming language. So there's three things it adds to C, three categories of things. One are compiler directives that you insert into your source code to tell the compiler how to break things up into chunks to run different processes. There are runtime routines. There are functions you can call from your code to set certain things up or to interrogate the machine about what's going on. So there's a set of library calls you can make. And there's also, it relies on, it'll use some environment variables that you'll set in your shell, right? So Unix, you have environment variables, and those are things you can set before you run the program. And inside the program, they'll affect how the program runs under OpenMP. So we'll talk about these three kinds of things, but those are the three ways you extend C to support OpenMP. Another reason it's popular is it's very portable. OpenMP was derived from, there was a effort in the sort of late 80s, early 90s to people started building, microprocessors got cheap enough that more people were building machines with multiple processors in. And all the vendors had their own proprietary ways of programming them. And there was an effort to standardize that. And over time, this evolved into this OpenMP standard. And now it's really a standard. So your same OpenMP program should run on platforms from Intel or ARM or Windows or these different operating systems or processor environments. So it's pretty standard. And it's pretty easy to use. You just compile, tell the compiler you're going to use OpenMP, and give it your regular C code and compile it for OpenMP. What's also nice is you can write it in a way that if you don't have OpenMP on your machine, but you have the OpenMP stuff in there, you can tell the compiler to ignore it and you just get sequential C code out. So it's pretty popular for that reason. It's quite a low level set of extensions. It's kind of like C itself. It's quite low level, but it's minimally intrusive. And this is a survivor out of all those dead programming languages. This one has kind of lived on. So the program model it gives you is, so we talked about the hardware, and OpenMP basically gives you a thin abstraction over that hardware. It says you program multiple threads sharing memory, and you have a lot of control over how it's parallelized. So the good thing about this kind of parallel programming is with shared memory, you don't really have to worry about where the data is, like physically in the machine. You just have to worry about a pointer to it, the address of it, right? And the compiler directives are pretty easy to use. And also what's interesting, because it's in C, you can take existing code you have for functions and just reuse those directly. You don't have to rewrite those. They just become C code within the body of one task, right? So you can reuse all that code you have already. One of the cons about it, it has to run in a shared memory environment. So OpenMP is restricted to a single node in a cluster, right? So if you have a cluster of 100,000 nodes like at Google, those clusters don't communicate through shared memory. They send the Ethernet messages to each other, basically. They communicate over the network. And so OpenMP won't run a single program across multiple nodes in a cluster. It requires that it's running on a shared memory machine where all the processors are sharing a single memory system. Okay, so that's one of the constraints of OpenMP. It also requires the compiler support this, but most of the modern C compilers do support OpenMP. For example, we'll be using GCC. So in 61C, there's really not a whole lot to learn. Once you've learned C, there's not a whole lot extra syntax to learn for OpenMP. When you write programs, what you have to include is this header file, openmp.h, and then you have to compile with this flag, -f openmp, when you invoke GCC. We'll go through some of it. But the thing to say is you're not going to become experts in this short time in the class. There's a lot to learn. You'll learn it better in the lab. You can't really learn programming from a lecture. You have to go do it. So you have some lab exercises to do that, as well as the project to work on this. So some of the key ideas that we go over in MP are shared versus private variables and all the different directives to tell the system how to parallelize your code. Okay, so it's probably easiest to start explaining OpenMP by explaining its programming model. And its easiest way to understand it has this fork join model. So if you imagine time running across this way, I'm running my code. I divide into regions where some regions there's just one thread running, the master thread. So you have a master thread, one of the threads is running sequentially, doing some work, setting up some work, and then at some point you go into a parallel region. And in a parallel region, you have multiple threads executing some pieces of some task in parallel, right? And this is a fork join model, so you hit say you hit a matrix multiply operation or something like that. At that point, you tell all the threads to cooperate, do that matrix multiply. Then when they're done, there's a join. They're all finished. Once they're all finished, you can go back to running one sequential thread to set up the next bit of code, right? So it has this model of a serial region, a parallel region, the serial region, then a parallel region. You have these fork and join, which is how you get from serial to parallel and back from parallel back to serial, okay? So kind of the master thread is always running. Once it enters this region, it just becomes one of the workers. But you only have these, inside the parallel regions is the only point where you have the parallel code executed. So the way that OpenMP programming works is you basically going to annotate your code with where do I want the parallel regions and some details about that parallel region. But otherwise, it looks like plain serial C code. So most of the C code just is sequential code run by the master thread. Then you hit some loop or something that you want to run in parallel. You just annotate that loop and say, do this in parallel. And the system will automatically split it up across the set of threads, this parallel region. And then when it's done, the system will also make sure all the threads come together, synchronize, make sure everybody's completed their task before you go back to running sequentially on one thread. Okay, so this is the basic OpenMP model. So these annotations are written as what we call pragmas in the C source code. So in your C text file, you'll add these additional statements that are pragmas. And these are written with a hash sign or pound sign, pound pragma, because they look like preprocessor symbols. You remember hash include and those other preprocessor symbols? Well, pragma is another example of that. And pragma is used for many other things, like how structures are packed, how symbols are aliased, how floating point should be handled. We don't cover those in C61C, but the same general mechanism, which is used for other things other than OpenMP, is also being used for OpenMP. And the nice thing about this is if a compiler doesn't recognize a pragma, it's supposed to ignore it. So if you write C code with OpenMP pragmas in there, and your system doesn't support OpenMP, it will just ignore the pragmas, and the model is then it just becomes sequential C code, right? So the nice thing is it's portable across systems that have and don't have OpenMP. So example of the simplest pragma, so here's hash pragma, then you have to follow it with the OpenMP symbol, OMP, and then say parallel. And what this means is for the following curly braces, all this code is going to be done in parallel by different threads in the team, right? So this says do this code in parallel across all the threads that are available, right? So I'm going to talk about how many threads are available in a minute. So every thread will run a copy of this code, and they'll just run it at some speed. So how many threads there are, each thread will run that code at some speed. But at the closing curly brace, the system will ensure that everybody's done with all the code, and then it'll continue back to being sequential code again. Right, so this is the simplest way of annotating a parallel section. As you see, this is very easy. Just hash pragma, do this in parallel. Here's your curly braces. This is the piece I want done in parallel. The one real tricky thing is that by default, all the variables that are touched inside that region are shared. So any location, if you have multiple threads running the same code, touching the same variables, they're going to be reading and writing the same locations in memory. And you have to make sure that's what you want to happen. Usually you'll want to declare a bunch of those variables private. That means that instead of having them be shared, I want each thread to have their own copy of that variable. We'll show some more examples to give you a bigger idea what this means. But the default is that everything is shared, right? You have to explicitly say that some variables are private if you want to keep them private to each thread. So a good question is, well, how many threads are there? You just said do that in parallel here. You didn't say how many threads I wanted to use. So OpenMP has a bunch of different ways of specifying this. One is with an environment variable that you create in the shell before you start running the program. So in the environment, you can have environment variable OMP num threads, and that'll tell the OMP runtime how many threads to use whenever it hits a parallel region. So for example, on the lab machines, you have 16 hardware threads. You might set that to 16. So every time you hit a parallel region, it's going to spawn 16 worker threads. They're going to run on the available hardware threads in the machine. And then when they're done, you go back to running on one thread. Okay. The thing to realize is that the OpenMP program is just a user-level program running on top of an operating system. Those threads it creates are just requests to the operating system for an independent thread. The operating system then decides, based on how many threads you want, how many threads somebody else running on the machine wants, or what other operating system tasks are running, how many cores you actually get and how many threads on each core. So the number of hardware threads you actually are running on at any point in time is going to change. In the best case, if you ask for 16 hardware threads and nothing else is running, every software thread will get a hardware thread to run on. But in reality, there'll always be something going on in that machine, so you'll see less than ideal performance. And especially if somebody else tries to run with 16 threads on the same machine, the OS is going to share. And on average, you only get 8 threads each. But in practice, you run much worse than half the speed because the OS doesn't know where your threads come from, and it may decide, for example, to run you need to wait for all the threads to finish. They may do them in some funny order. You have to wait a long time for all the threads to finish in one section. Right. So basically, when you're timing results for Project 3, make sure nobody else is running on your machine, because the OpenMP threads are just software threads. The OS is mapping those to hardware threads, and it can mess up your timing. So as well as setting things by the environment variable, you can also do it in the program as it's running. So there's a function call to explicitly set it in the code as it runs. Right, this is an alternative way. You can say set num threads. Inside the code as well, there's library calls you can make to request. I want to know how many threads I do have. I'm supposed to be using get num threads. Another important call is you can ask which thread am I. So get thread ID. Right. So you hit a parallel region. All the threads start running. Each thread, a common thing to do is ask, well, which thread am I? And you need to know that so you know which piece of the parallel work should I be doing, right? You don't want all the threads doing exactly the same work. That'll be redundant. Each of them, based on their thread ID, is usually going to pick some different piece of the problem to work on, right? So the get thread num tells you which thread you are. Okay, so let's do a simple hello world in parallel. So this is the OpenMP program. So you include stdio.h, just the regular header file to do I/O. You also include openmp.h. That's another standard header file for OpenMP. So here's a couple of variables: number of threads, thread ID. We're going to fork a team of threads and say pragma OpenMP parallel. And this is a base declaration. We're also going to say, let's make thread ID be private. We declare thread ID up here, right? But we want each thread to have its own thread ID. So you have to say explicitly to the system, create a separate copy for every thread inside that parallel region, right? Otherwise, they would read thread ID in some order, but all of them will think they were the same thread, right? Because you overwrite the same variable thread ID. By saying private, each thread gets its own copy of that variable, okay? So now, first thing the thread does is find out who am I. So thread ID equals OpenMP get thread num, and then you can say print out hello world from thread ID, right? So that's going to print hello world once from every thread that's active in that parallel region. Okay. Now notice here you say if the thread ID was 0, we've designated thread 0 to be the master thread, right? It's going to print number of threads here. How many threads were there in total? And just do this once, okay? And then this is the closing brace for this pragma. So at this closing brace, all those threads come together, finish, and terminate, and then you can exit the program. So this program is going to print out, say it was running on that 16-thread machine in the lab. It's going to print out hello world from thread 0 through to 15, okay? So there'll be 16 of those print statements saying hello world, and there'll be one print statement saying the number of threads is 16. Now, what order will those print statements happen in? I get 16. Right, it's non-deterministic. So you'll get the printouts from the different threads happening in any order, right? And another important thing to realize is you may get this number of threads thing may be printed right after one possible order is hello world from thread 0, number of threads equals 16, and then 15, 14, 13 comes back in some order. So the threads, how fast they run is not specified relative to each other. So it's non-deterministic, right? And if you think about it, this makes sense because this frees the operating system. It can run all 16 threads. You can ask for 16 threads even if you only have one hardware thread. And the operating system is just going to say, okay, I'll just run one at a time until they're done in some order, right? So the order the threads run relative to each other is not defined at all. So you have to make sure, and we'll talk about how to do this, that you synchronize the threads. If you need some kind of ordering between the threads, you have to explicitly code that in yourself. The default is they just run independently until they get to that join point when the parallel section is done. Then you're guaranteed everybody is done at this point, but in between these 2 points, they're all just running non-deterministically separate from each other. Okay, that's the programming model. Now, one of the ways this shows up, this problem shows up is if 2 of the threads are accessing the same memory location, the shared memory location, and one of them is doing a write, then we have what's called a data race. So the problem here is, one of them is going to write, they're both going to read the location, and you're not sure what order the write is going to happen relative to the read. It's a race because it depends on who gets there first, what values you're going to see in the resulting program. And so the problem is then the result of your program will change depending on just what happened in the machine when you're running it. And that's not usually a desirable property. Usually you want the program to give you the same answer every time you run it. You want a deterministic result every time you run the program. And to make sure that happens, you have to explicitly synchronize, like I said, the different threads. And so that's actually done by user-level routines that you add to synchronize the different threads. So here's an analogy to give some idea of what we're talking about. You got no milk in the fridge, okay? You and your roommate both come back from classes, one at a time, check the fridge. You both realize there's no milk in the fridge. And you're both good roommates and decide, well, if there's no milk in the fridge, I'm going to go buy some milk in the fridge. So you end up buying two jugs of milk, right? Right, and so the answer is, well, one of you should have left a note, right, to tell the other one, I already got the milk. But that's a simple example, real-world example of a data race, right? Parallel systems, 2 users, 2 people, go into the fridge. You do the same task twice because you didn't realize somebody else already started on that task. Okay. So in the computer world, when you have something like that, that's an example of there's something that should only be done once, right? But because you didn't provide any synchronization, it got done twice, which is the wrong number of times, right? You only want it done once. So a critical section is a phrase for a piece of code that you only want to execute once. And the way you ensure that only one thread is in there at a time is by adding what's called a lock. So the idea is the first thread that gets to this critical section will take a lock on it, and no other thread is allowed into the critical section while the first thread holds the lock. When the first thread is done doing whatever it does, it will then release the lock. So the analogy here, I go to the fridge, I realize it's empty, I put a lock on the fridge. I get to the fridge, I lock everybody else out of the room, while I check the fridge. Nobody else is out in the kitchen. I'm going to check the fridge, find out it's empty, keep the kitchen locked, run to the supermarket, come back, put the milk in the fridge, then unlock the kitchen, right? Then whoever else comes along, they're going to see either there's no milk and nobody is going to get milk, or there is milk and I don't need to do anything, right? Okay, so think of the lock as locking the kitchen. So the way we actually implement locks in these shared memory systems is by just using a memory location, right? So lock is just the location in memory that has a value that you agree upon to represent something that the critical section is locked. So the idea is you're going to, before you try and enter the critical section, each processor independently is going to check the lock first and see, oh, is somebody else already in the critical section? If so, I'm going to wait until they're done, just by spinning and rereading the lock location again and again until I see that it's cleared and nobody else is in there. Then I can enter the critical section. Okay? So the idea is you're going to check this memory location to see if the other guy's in there. So we can use a protocol. Usual value is 0 means the lock is open, lock is free. Any non-zero value, 1 or more, means that the lock is taken and you have to wait for the critical section. Okay, so this is kind of the pseudocode for doing this, right? So I'm going to check the lock, and I'm just going to loop. If it's set, I'm just going to loop around and wait for the lock to be cleared so the lock is open, all right? But as soon as I see the lock is cleared, I'm going to lock it, enter the critical section, do whatever I want to do, change some shared variables, then unset the lock and let somebody else in, okay? So that's kind of the general pattern of what you want to do. Let's now think about, well, how do I actually write the code for this, or how do I run this on the machine? Let's dive all the way down to assembly code level and think about implementing this. So in MIPS assembly code, you're going to put 1, let's just write 1 into T1. That's going to represent the locked value. You can do a loop where you first load the value of the lock. So S0 points to the lock. Load the value of lock into T0. If it's not equal to 0, that means it's locked. So I'm just going to spin in this loop, just repeatedly reading that memory location and spinning around in the loop, right? Finally, at some point, it becomes 0. I drop through. I store 1 into the lock. At that point, I've got the lock. It's locked. Then when I'm done, the unlock is very simple. I just write 0 to that memory location, right? That's how you unlock. So, yep.
What would happen if two things, when they're checking the lock, they both check the lock at the same time, and then one of them says,
Right. Great question. So what happens if two threads come along and both do that load word at the same time, or one after the other, before the guy said them? This is exactly like the fridge problem, right? They're both going to, think, oh, the fridge is empty. I've got to go get milk. So this won't actually work, right? And this is, showing you a possible interleaving that will not work, right? So here's thread 1, here's thread 2. Say thread 1 does this add, then this load. It gets the value of 0. This guy does this add, this load, gets the value of 0. They both think the lock is open and they can grab it. So they fall through. This guy stores 1, this guy stores 1. Now they're both in the critical section, and that's not what you wanted to have happen, right? So using the regular load and store instructions is not going to work, because the two threads can execute those. Remember, you don't know how fast they run relative to each other. In fact, what can happen is, even if you run these two threads on one hardware thread, if there are two software threads running on one hardware thread, you can still get this problem, because the operating system may come along just after you loaded that word and found it was 0. It may swap you out, then start running this guy, right, then swap this guy back in. So even if there's only one actual hardware core, you can still get this problem. Both of them thinking they got the lock, right? So this doesn't work as a way of providing the lock. So actually, it turns out this is a case where we need to add new hardware support and actually new instructions to the computer to support this kind of synchronization. And the thing we added what's called atomic read-write operations. So the problem is that from the time we read the value and saw that the lock was open, free, to the time we set the value grabbing the lock, somebody else could get in and read the value and think it was free. Right? And what we want to do is provide an atomic read and write where we read the value, see that it's clear, and set the value without allowing any other processor in the meantime. So those are atomic read-write instructions. And what's interesting is if you look at different computer architectures, they've all done this very differently. So there's probably like 20 or 30 different ways of doing this. And people argue at length about the best way of doing this, and they still argue. It's not like it's a done, settled deal. So the way that MIPS does it is a technique called load link store conditional. And these are two new instructions you add to the instruction set. A load link is kind of like a load, but it kind of puts a reservation on the address. Store conditional is kind of like a store, but it's conditional that the store only succeeds if nobody else touched that location in the meantime. Okay, so we'll go through how this works. So first of all, the way the instruction format, load linked, has a base address and an offset, just like a regular memory operation. It has one register that is gets the result of the load. So the load link does a regular load operation, but it has this side effect of saying, I'm putting a reservation on this address. Tell me if anybody else touches the same address. Okay, so load link just grabs the location, grabs the value, and puts a reservation on it. Store conditional has this register, which is both the data that you store to memory, but this store, unlike regular stores, returns a success value back into that same register. And it says the store conditional, the store only takes place and updates memory if nobody else touched that reserved address meantime. So between the load link and the store conditional, if nothing else touched the same address, store conditional will succeed, the data will be written to memory, and you'll get a success value in the RT register, right? So an unfortunate thing in the way MIPS define this is that the store conditional actually overwrites the store data value with the success value. So it's used both as a source and a destination in the MIPS instruction encoding. That's unfortunate, but that's what they did. So you have to kind of keep it around somewhere else to copy it back in again if you need to repeat that store conditional. So let's see how you would use this. So now let's try building the lock example again. So so this is the value that you want to write into the lock. We're going to load link from the lock location into T1. And then we're going to try conditionally storing this back in there. So this is very tight load link store conditional. So load link, remember, loads the value and puts a reservation on the address. Store conditional only succeeds if nobody else touched that address meantime. And if it does succeed, you get a success value in T0. And here you're trying it out. If you fail, like if you find out that you didn't get a 1, you got a 0, you just repeat the whole sequence. So you go back and repeat the load and repeat the store conditional until nobody else is interleaved in there. Then you know you're done and you've atomically grabbed that lock. Okay, and this just moves it back into S4. I don't know why that's there for. Okay, anyway, so this grabs the lock. I guess this just gets the value from T1 into here. Oh, sorry, this is doing a swap, right? Okay, this piece of code is actually atomically exchanging a value in a register with a value in memory, right? So swapping two values. Okay, people see how this works? Yep.
So you're saying that a success value should be stored into T1? Where is the success value?
So, okay, so maybe explain a bit more on this. So load link, this address, the result of the address computation, the effective address, the offset plus the base, that's the address that you're reserving. And you can only reserve one address at a time. You can't have a whole string of load links reserving hundreds of different addresses, right? It's a very restricted instruction. It just says this one address is the address I'm reserving. And I'm going to execute some following instructions. And when I do the store conditional, it has to be the same address. And if that same address has not been touched by any other processor, then the store conditional will succeed. And if it succeeds, it overwrites the data operand, in this case T0, with a 1 to indicate it succeeded. If it didn't succeed, if somebody else touched it in the meantime, that'll be a 0, and the store won't happen. So the store won't take place. It won't update memory. It will only update memory if nobody else touched it in the meantime, and it'll tell you the success variable. Yep.
So if you have two threads that are kind of access the same thing, one can continually say that another thread tries to access it and keep on granting.
Right, that's a good question. The question is, does this suffer from what's called live lock? So what happens is, I reserve this address, you reserve this address, kicks me off, and before you get to store conditional, I reserve it again and kick you off. So you're kind of both kicking each other off the reservation before you get to do the store conditional. That is a valid concern. It actually is an issue with this style of machine. And the reason it's not a big problem in practice is that these sequences are usually pretty short, and the processors are relatively far away from each other. So usually by the time you die, you grab it from somebody else, and you can then complete before they get around to trying to bash on you again. But it is actually a genuine concern that some machines will live lock if you have the right setup. Yeah. So, yeah, so people try and build, there's a notion of a queuing lock. where instead of everybody bashing, trying to, once the lock gets freed, what happens is everybody goes crazy trying to grab the lock. If you have many threads contending for this one lock, a better strategy is somehow queue them up so there's an orderly line to. However, it turns out building that needs something atomic at the bottom. So you can build that better synchronization structure on top of something, but at the base you need something that provides atomic read modify write. Yeah, I don't understand the question. Well, remember, so to pop up a level, remember what we're trying to do here is implement a critical section, which is a piece of code that only one thread at a time should execute. So getting back to the fridge analogy, you just want one person to get the fridge from the supermarket. You don't want to paralyze that operation, right? You don't want 100 gallons of milk showing up, right? So you just want 1 gallon of milk, and then you're done. And everybody else that comes along and looks at the fridge knows there's milk, right? So this is about actually sequentializing the execution in a controlled way, because there should only be one thing happening at a time. So we're not trying to make things parallel. It's exactly the opposite. We're trying to make things happen one at a time in the critical section, right? So that's the purpose of this. So another thing to realize is that the reservation you grab, so this load link reservation, the hardware is free to drop it for whatever reason is convenient to the hardware. So for example, if you get an interrupt and the operating system wants to swap you out, you don't keep your reservation, you lose it. And so, if you did this load link here, and right here the operating system swapped you out and ran a different thread, the system will just cancel your reservation. So when you come back to the store conditional, it'll just fail, and you just retry again when you come back around, right? Yep. Yes, that's right. So the comment was, if you had a critical section with two people, like say the fridge is empty and somebody gets milk and somebody gets chocolate milk, or 1% or 2%, depending on who gets there first, right? So you get different outcomes depending on who got to the fridge first, right? And that's right. And one of the problems you have is programs that they're actually a class of programs where it's okay. Different results are fine. They're just different. They're both the right answer. For example, say I want to build a data structure that holds a set of all the students in this room. I don't care about it being sorted. I could have some parallel structure that searched the whole database of the Berkeley campus, found all the students taking 61C, and inserted them into a set object. I don't actually care for correctness what order people are in that set. I just care that they're in the set or not. That would be an example of a program that didn't have a single legal answer. There were multiple satisfactory answers, and you would get different answers based on timing. So the program would be correct. The problem is it's really hard to debug that kind of program, because you run it once, you get a bug. You run it again, the bug's not there because something different happened. And so when you don't need that flexibility, usually try and make programs have one reproducible answer, because it makes it much easier to debug. But in practice, there are some cases where you don't care about the ordering. And yes, you'll get different actual answers from your program. One example is the Hello World example. Hello World is going to print from each of the threads the results in different orders depending on how the threads are scheduled, right? But maybe you don't care. All you care about is seeing Hello World from every thread. Yeah, so you will get different ordering. This is one of the reasons why parallel programs are harder to write and debug, just because sometimes a valid program does do different things every time you run it. And it will vary depending on the temperature, right? So if the room's hot, your processor's hotter, some cores are running hotter, and the operating system moves things around. So yeah, literally can depend on the temperature. Let's try and look at doing test and set. So test and set is another one of these, all it is test the log variable if it's 0. If it is 0, set it to 1. Okay. And so just basically seeing how to do this in MIPS code, right? So test and set is, load the value, load the lock variable. Is it unlocked? Yes. Try to grab it. Were you successful? No. Try again. Successful? Yes. Keep going on. Unlock it. So this looks a lot like we had before. So you put a 1 into T0. You load linked the location of the lock S1. If you find that it's not 0, that means it's locked. Repeat. So you're just going to repeatedly going around here trying to do load locked. One thing I should have mentioned. You only need to fail the reservation when you see a store to the same address, right? It's okay to have multiple people think they have reservation on a load, but it's the first one that does the store that wins, right? Because if it's just reading the same value, nothing, that's okay. It's only the store that you have to worry about. So that means the live lock is also less likely. It doesn't get rid of the live lock, but it's only a store that will cancel the reservation on all the other processes, right? So if multiple of them have a load link, can have a reservation. Okay, so test and set. Put a 1 into T0, read the value of the lock and link and reserve it. If it's locked, just try again. Repeatedly do this. If it is 0, try and execute the store conditional. And you may fail here, right? If you fail, you have to go back and retry. Right, notice here I keep putting the 1 back into T0 as that's the value I need to store in the lock. So T0 is the value 1 is the value I want in the lock, but also that register gets overwritten by the success value. So when I go back to try, I have to re-put 1 back in that T0 register. Once I succeed and drop through here, I'm in the critical section. I can do this knowing that nobody else is in the critical section. Then when I'm done, I just unlock it just by writing 0 out to the lock variable. Okay. Question? Right, it's a good question. So if 2 threads simultaneously do a store conditional, which one wins? The answer is, well, only one of them can win, or should win, and the hardware will make sure that only one of them wins. And it just has an arbiter in hardware that will decide if these 2 are going for the same memory location, I'll let one of them through. You need that anyway, because you can't really let both of them write different values on the same clock cycle. So one of them, the hardware is going to sequentialize that some way, so one of them will win. Okay, so this is how to do a simple lock. It just tells you where those pieces come from. Yeah, one thing to say about this lock stuff. So most programmers should not write lock code, because sort of 99.999% of programmers cannot write correct lock code. It's very, very hard to get it right. Even very skilled programmers shouldn't write lock code, because they're not as skilled as they think they are. When people were developing this stuff, there was a whole string of papers from very famous theoreticians about how to do this correctly, and they were usually wrong. And the next year, somebody published a paper saying that guy was wrong, and this was the bug in his code. Here's my code, and then a year later, there'd be a bug in that code, right? And so this went on for a while. Still goes on. This is some of the hardest code that people write, is making locking work correctly and at a high speed. And so almost no programmers touch this code, just people writing operating systems and people writing libraries. Most programmers will only touch this stuff through libraries, because actually writing this low-level assembly code and making it work in all cases is incredibly difficult to do. Clicker time. Okay. So this is getting at this comment before that when you're running parallel code, sometimes there are multiple possible results possible. And this is asking you for this piece of assembly code that's run at the same time by 2 different threads, touching the same memory location. What are the possible end values in once they're both finished? What are the possible final values that could be in the memory location? Someone's hacked the clicker. Yeah, I never knew the class was that popular. Okay, so I guess somebody's hacked the clicker system. So the important question is, did the bug you exploit, was it a race condition that wasn't properly synchronized? I don't know. It's what? I don't know what happened. Somebody probably hacked the system. Either that or the system's broken. Okay, well, either the system's messing up or somebody's messing with the system. So let's do the show of hands. Who has 2,000 hands to put up? Okay. Who thinks A? Right? Who thinks B? Who thinks C? Who thinks D? Okay, yep, it was A, right? So they're going to either add 1 to it, or they're both going to add 1. You get 101, or one of them's going to add 1, the other one's going to see that and add another 1. So you're going to get 101 or 102. Okay, so actually, let's just do this next time, okay? See you next time.